This is basis vectors, the definitions below. A basis vector for a vector space V is linear independent set of vectors that is a spanning set for V. As we've already been through what spanning sets are. If you've not seen that or you don't know, I'd recommend going back and looking at that one, which should be clearly labelled within a playlist. Now, to determine whether a set of vectors S is in a vector space V is a basis for V, we check the following conditions. 1. S is linearly independent and S spans our vector space. Now here's an example. We'll show that this set here is a basis for our space. So we'll check for linear independence by writing all these components equal to 0 and equating when we multiply out. And again, which this should be familiar by now, we're equating all these to 0, and in order to find the values for alpha, beta and gamma. Now we substitute third equation from first to give gamma equals 0, and substitute this into the second equation gives beta equals 0. Substitute this into the first gives alpha equals 0. So indeed all of these components are 0, so this means it's linearly independent. Now we need to show that every vector in our space can be expressed as linear combination of the vectors in S. So we show that the general vector xyz can be, each vector in our space can be written as xyz with xyz contained in the reals, and to show that is in S, we write it out again and equating again, subtracting the third equation from the first gives gamma equals x minus z, and substitute this second equation gives beta equals y minus x plus z. And we finally substitute beta into the first equation, which gives our alpha value here. Now we have a solution for any vector in our space, and it can be written as such. So S spans our space, and since the conditions hold, the set S is also a basis for our space. Note, standard basis for R to the n, our general case, is the set of vectors. These are standard basis. So our sets of vectors 1 0 0, so on 0 1 0 0, and which is pretty common sense kind of stuff, as you would have no doubt seen the kind of notation for unit vectors. Well, this is the equivalent, should we say. So and examples here in P of n, which goes up to n minus 1, or in matrix interpretation here, these are standard basis for matrix or complex numbers 1i, and this is the basis for that. And we note that dimensions here and here and so on, which you can just follow the pattern and keep expanding the dimensions. So that's standard basis. Now please do like and subscribe, there's plenty more to come.